CNNs, or convolutional neural networks, are a class of deep neural networks primarily used in processing data that has a grid-like topology. Examples include time series data, which can be thought of as a one-dimensional grid taking samples at regular intervals, and image data, which is a two-dimensional grid of pixels. The CNN's ability to automatically detect important features with little pre-processing, reducing the need for human intervention, distinguishes it from other data analysis techniques. Essentially, CNNs manage to transform raw data into layered information of increasing abstraction, making them particularly effective for problems like image recognition, where the machine can learn to ignore irrelevant variations in the data and focus instead on discerning patterns. Thanks to gatekeeper functions known as activation functions, each neuron within the network can decide how much of the information received is passed further along, mimicking, in a very limited sense, the neural processes of the human brain. The architecture of a CNN is defined by layers that work together to understand input data in deeper ways than traditional algorithms. The primary layers include the convolutional layer, the pooling, or subsampling or downsampling layer, and the fully connected layer. Each layer plays a specific role. The convolutional layer, applying mathematical operations known as convolutions, identifies features such as edges or textures in images. This is followed by pooling layers that reduce dimensions but maintain the most important information, thereby optimizing computation and also providing the model with translational invariance. The fully connected layer, akin to traditional neural network layers, uses the high-level reasoning from the convolutional and pooling layers to classify inputs into various categories based on the learned features. Distilling the operation of CNNs further, each component, from kernels and filters to strides and padding, plays a pivotal role. Filters in the convolutional layers are essentially small matrices applied repeatedly across the entire input, forming a feature map that highlights where certain features are located in the input. Strides dictate the filter's movement across the input image. A stride of one moves the filter 1 pixel at a time, while a larger stride reduces computational load but may miss subtler features. Padding involves adding layers of zeros outside the input to allow the filter to fit around the edges, thus preserving information located at the borders of the input. These components are optimized during training via a backpropagation algorithm that adjusts filter values, weights, to minimize the error in output, streamlining the network's performance over time. CNNs have found applications across a broad range of industries. In healthcare, they are used for tasks such as diagnosing diseases from medical imagery. In automotive, they power the vision systems of autonomous vehicles. In retail, CNNs analyze consumer behavior through surveillance footage. Each application leverages the CNN's ability to extract patterns from complex, multi-dimensional datasets, allowing for precise predictions and decisions. The adaptability of CNNs to different data forms and their capacity for feature recognition make them invaluable in settings where traditional data analysis methods fall short. Despite their capabilities, CNNs face significant challenges. The training process for CNNs, for instance, demands substantial computational resources, particularly data storage and processing power. Overfitting, where a model is too closely fitted to a limited set of data points, is another challenge. It impedes the model's ability to generalize from its training data to real-world applications. Moreover, the opacity of CNNs, often described as black box models, poses an ethical dilemma, making it difficult to discern how decisions are being made, which is particularly concerning in sectors like finance or law enforcement. Professionals and researchers are continuously working to surmount these hurdles. Recent advancements include techniques like dropout, which randomly drops out a portion of neuron outputs during training, helping to mitigate overfitting. Another is the development of more sophisticated hardware designed specifically for deep learning tasks, such as GPUs and TPUs, that speed up the training process. Additionally, transfer learning and few-shot learning approaches enable CNNs to learn from a smaller amount of data, broadening their applicability without the previously required vast datasets. To illustrate the application of a CNN, Consider a simple image classification task where the objective is to differentiate between images of cats and dogs. The CNN is trained on thousands of labeled images of cats and dogs. During training, the network adjusts its filters to better recognize the features, like fur texture or ear shape, that distinguish one animal from the other. Upon completion, when a new unlabeled image is processed, the CNN uses its learned features to predict whether the image is of a cat or a dog, demonstrating its powerful pattern recognition ability. CNNs have fundamentally altered the landscape of artificial intelligence applications, driving innovation in an array of fields through their capacity to interpret complex and substantial data sets. While they present certain challenges, ongoing research and technological developments continue to push the boundaries of what is possible with CNNs. As we improve our understanding and enhance these networks, the potential for AI to effectively partner with human endeavors grows significantly, promising a smarter and more connected future. Moving to how our platform To the Moon with AI harnesses these powerful networks, we offer ready-to-deploy machine learning solutions tailored for sectors including finance, engineering, automotive, environmental management, and physics. These solutions accelerate and refine the precision of computational processes, increasing efficiency and reducing operational costs. Don't forget to subscribe to our channel, hit the like button, and click the bell icon to stay updated on all our latest content. Visit our website at tothemoonwithai.com to explore our ready-to-deploy machine learning solutions that are specifically crafted for your industry needs. Empower your business with cutting-edge AI technology today. Thank you for watching, and we look forward to helping you innovate and excel with AI. See you in our next video.